Thank you. Thank you for that great and entertaining introduction. I recognize a lot of your faces in the audience. I can't really see the faces on the video, but at least here I know I've seen quite a few of you in other classes and other events, and another pretty good-sized chunk from the Hampton Inn across the street this morning at breakfast. So I would like this to be very interactive, so people should feel free to ask questions at any point. In fact, if there are questions that are left over from earlier talks that relate to Fermi or architecture and hardware that you didn't get answered, we can start with those before I jump into it. If you have a question in the remote site, just say, we have a question, and I'll pause. Okay, and John will moderate? Okay, and John Stratton will be the traffic cop, so respect him. Okay, so any questions on your mind from before I launch into what I prepared? Okay. All right, I'll start. So I'm going to talk about the Fermi architecture, the hardware that we've most recently built, and I will talk about it in terms of, at a high level, how we think about GPU computing architecture, and in that context, Fermi is just a specific implementation in the series, in the family. And as always, when we build a new architecture, we build a whole family of chips from very high-end to low-end laptop, low-power versions. And they're all architecturally similar. They share the same features, they share the same overall functionality. They differ only in cost, performance, and power consumption. But the programming model maps cleanly from top to bottom. Okay, so overall, I'll start with general GPU hardware. Probably most of this is familiar to you, but maybe some of the ways I will describe the abstraction will be useful for you. Some details about Fermi, and associated with Fermi, we have a bunch of new software tools and libraries and some new programming language support that I think will continue our march toward making GPU computing and GPUs easier to use for solving application problems. So starting with hardware. At a high level, this picture in the lower right is really the right picture to have in your mind about what a GPU looks like. We used to draw much more detailed and complex diagrams which showed all the connections and showed all the little functional units inside. And I think it was nice from the point of view of full disclosure and giving people all the understanding to be able to do everything they needed to do with the machine. But on the flip side, I think the more detailed architectural diagrams led people to over-optimize for specific features or specific idiosyncrasies of a particular product generation, so that as we evolve forward and we make some optimizations and some improvements, some of the side effects that people were optimizing for no longer existed. So I think a higher level view is better, just looking at a GPU as a collection of multiprocessors. And this can be, in the current family, it can be a very small number, as little as one, or even a half of one that will take multiple clocks to go through doing its tasks, to tens of multiprocessors. We don't have any architectures with hundreds of multiprocessors yet, but it won't be long. We'll get there too. And we use the term multiprocessor because it's not just a processor. It is a processor that executes groups of threads together. So we talk about that as co-executing a group of threads. And you can't really think about an individual thread being executed on a GPU multiprocessor. All the efficiency and all the organization of work is for groups of threads, warps and blocks to be executed together. And then the other component is memory and the memory hierarchy. And so there is DRAM external to the GPU chip, and there is a cache hierarchy and some on-chip scratchpad managed memory to mitigate the burstiness and the granularity of accessing the external RAM. The caching is new to Fermi. Previous generations did not have a fully instanced L2 and L1 hierarchy, and that's a new feature. So each multiprocessor, which shows up in this diagram as a SM, streaming multiprocessor, has its own control unit for decoding and issuing instructions, and scheduler that schedules threads in these groups. The control unit is separate from the execution pipelines, so there can be different numbers of control units and execution pipelines depending on how we balance the system. That's one of the things that is a detail, an implementation detail that can change, that we would rather people don't optimize for on a particular piece of hardware. But we have separate pipelines for integer 32-bit and 64-bit floating point, special functions such as square root, sine, and cosine. And multiple instructions can be issued in the pipeline in the same cycle, and it can be in any combination of these different pipelines within the SM. There's registers for each thread. When a block is launched on an SM, the registers and other resources are statically assigned to that group of threads, and they remain the property of that group of threads for the lifetime of that block. Same with shared memory that is designated as part of a block. Shared memory is physically shares the same silicon as the L1 on Fermi, and it's really, the way to think about it is it's a scratchpad or user-managed cache. So if you know which data you're going to be using, and you know what the lifetime is, and you know what the granularity and scope of access is, using shared memory is a powerful technique, because you can do a better job than any cache strategy implemented in hardware, because you know your application. Whatever your application is, I'm sure we haven't anticipated it in our cache design. So the L1 cache sits between the SM pipelines and the L2, and L1 is not coherent between SMs. The L2 is shared between the SMs. So what's in L1 is all local to the individual threads that are running on that SM. The texture unit is still available for GPU computing, as it continues to be important for graphics. It's something we devote a lot of hardware and a lot of effort to making it efficient. It is a separate and parallel caching system, and it's also hardware managed. And it has built into it a bunch of really nice interpolation and type conversion hardware, because we need that for graphics, so it's available for free for general compute operations. Okay, so that's the general picture. The SMs run instructions just like any other processor, in the sense that we issue instructions and we execute them and then we move on. But there's some differences and some choices that we made. we've made the choice to, as much as possible, keep the multiprocessors very, very simple compared to a modern microprocessor, which has tremendously deep pipelining, speculative execution, out-of-order execution, all kinds of ways to determine how you can execute always an instruction every cycle or multiple instructions per cycle out of a single thread. We don't do any of that. None. We execute, for a given thread, we execute the next instruction if it's available, if it's ready to execute. If it's not, we might execute instructions from some other thread. And again, this is done in groups of threads. And we still have 32 wide warps in Fermi. And that's 32 consecutive threads in terms of thread ID. But this number is not guaranteed to stay the same over time. The warp is simply an implementation detail, and you should think of it in terms of it's a vector of threads as opposed to a vector of data. If you have a vector of machine, it typically would be a vector of data which you operate on. A warp is a vector of threads, and it's just a way for the machine to consume chunks of work rather than individual granules of work. So next time around, the size of a warp could be 64, or it could be 16. So your program shouldn't rely for functionality on the warp size. Only for performance, you should think in terms of grouping similar work in warp granularity. And it's always better to have your similar work grouping be larger if you can. Because at some point there's going to be a machine that can take advantage of 64 or 128 or 256 wide warps someday. I don't know how long. That'll be a while probably, but it's good to think in terms of that coherence of execution. So right now in the current implementation, and in all the ones so far, 32 threads will execute the same instruction. So we have a single control unit that fetches and dispatches the instruction, and then all 32 of the threads will run that same instruction. And although that's the execution model, the programming model is fully MIMD. Each thread can execute a completely different code path. You could do a 32-way branch with all the threads that are in a warp, and it would run just fine. It would run slowly. In fact, it would run 32 times more slowly than having all the threads execute the same instruction. But it would just work. You wouldn't have to worry about functionality. So that's why I say don't think of the threads in terms the warps in terms of functionality. Think of it in terms of performance. The hardware will handle all the branching or predication. We can do predicated execution if it's a short branch. But it's always going to cost performance when you have divergence of execution within a warp, because the whole warp marches in lockstep, and the only ability we have to execute different instructions for parts of the warp is to run the warp twice, to run it once for the threads that took path A and once for the threads that took path B until they converge again. Then you can run just a single instruction and capture all of the threads. So if you structure your code with your branching, if the branch granularity is greater than 32, then all the threads in the warp are likely to go the same way, and you're much more likely to get efficient execution. And then threads in different warps can take different code paths, and that causes no performance degradation.